In the previous two videos, we were focusing on EUV and optical systems as a whole, the past systems and the present system. In this video, we will have a closer look at the manufacturing technologies that make these systems possible. The stable performance of the optical system can only be achieved by applying leading-edge technology and a controlled production of its components. After the raw optical material is being produced at the supplier, the blank material arrives at the factory at size. The first production step that the blank material sees is the optics production. Let's have a closer look at that. And this is how an EUV mirror looks like. The first step in the optics production is generating the basic shape of the mirror. Depending on the material, grinding or milling tools are used. Roughness reduction is achieved by polishing with large tools. Choosing appropriate polishing slurries and polishing pads is crucial. A full mirror specification will typically be below 100 picometer RMS. This error contribution represents the total effect on the system wavefront caused by a single mirror. But the total error budget of the component consists of contributions from surface metrology, surface machining, inhomogeneities of the multilayer coating, coating tension, deformations induced by assembly, and thermal and aging effects. As a result, a total requirement for the repeatability of the measurement in the order of magnitude of 10 picometer is needed. Very low values of the thermal expansion coefficient are important for EUV mirror substrates. Only 70% of the incoming EUV intensity is reflected, while 30% is absorbed in the mirror material and transformed into heat. Since the whole EUV system is built up in a vacuum chamber, the heat transfer from the mirrors to the outside is very limited. During operation, a temperature rise of a few Kelvin is not unusual for EUV mirrors. This results in surface deformation, and this mirror heating makes zero expansion materials mandatory for an EUV mirror. Computer-controlled figurine technologies are used for figure correction. Based on the error maps from the full aperture interferometers, they shape the surface locally. Various technologies, as for example computer-controlled polishing and ion beam figuring, can be used here. Metrology is an integral part in the fabrication process of the mirrors. While the polishing process is basically a relative process in which material has to be removed in each polishing step, metrology has to provide absolute deviations from the required shape. Figuring processes and metrology form a closed loop of iterative steps. The real challenge is to control figure quality simultaneously with the mid-spatial frequency roughness MSFR and the high spatial frequency roughness HSFR. The metrology for the production of EUV mirrors has to cover the complete spatial frequency band, reaching from clear aperture down to 10 nanometers with accuracies and precision on atomic scales, without leaving any frequency gaps. Figure is assessed by full aperture interferometers, equipped with dedicated compensation optics to deal with the aspheric shape of the surfaces. These instruments yield 2D surface topography maps. If the design figure is not met, aberrations are induced, usually seen as CD uniformity errors or overlay errors due to the long-range nature of the figure. MSFR is measured by microinterferometers. Bad MSFR leads to light that is scattered into the illuminated field, which leads to bad uniformity and bad contrast for the system performance. HSFR usually is covered with scanning atomic force microscopes or AFMs. Too much ASFR leads to reduced reflectivity and system transmission. Data of all three metrology tools is then merged and digested into a continuous PSD of the surface, covering the complete relevant frequency range without any gaps. The increase in resolution due to the short EUV wavelength is accompanied by extremely challenging requirements for the surface tolerances of the mirrors and will be discussed based on a rule of thumb. Aberration-driven wavefront errors are usually specified in units of the wavelength lambda. For a single surface, the aberrations are given by n-1 times delta H over lambda, where delta H are the topography errors. Here, the refractive index of n is approximately 1.5 for a non-immersion lens surface, and n is -1 for mirrors. Therefore, mirror surfaces are generally 4 times more sensitive to surface errors than lens surfaces. In addition to the increased sensitivity of mirrors as compared to lens surfaces, also the short wavelength itself enhances the implications of the surface topography. The total wavefront error for all lens elements has to be multiplied by the square root of n. N is the number of optical surfaces. For an EUV system with 6 mirrors having the same wavefront quality as a deep UV system with 60 surfaces, the surface quality requirements scale like this. The requirements on low figure errors are approximately 20 times tighter for EUV surfaces. This table summarizes the key performance improvements for figure, MSFR and HSFR on mirror level over the different size EUVL tool generations. The sizes of the mirrors became significantly larger from tool generation to tool generation. At the same time, the surface performance requirements have continuously been tightened with each EUVL tool generation in order to comply with challenging imaging and throughput specifications. The MSFR roughness has improved by a factor of more than 3. In order to keep the OPC effort within reasonable limits, nowadays a flare target of below 4% is required and indeed achieved for 3300 and 3400. To visualize what these specifications on a mirror mean, you could use the following analogy. If you would inflate the size of a single lens element to the size of Germany, the tallest height or the tallest mountain would be roughly 100 micrometers. After the polishing of the surface is finished, a multilayer coating is deposited onto the surface. The EUV coating is the only element that is interacting with the UV light. Therefore, the coatings are the only elements in the whole structure of the scanner that are optically active. A typical EUV coating consists of around 50 bilayers of molybdenum and silicon. Together, they form a so-called Bragg reflector. The reflectance curve over wavelength of such a coating is usually roughly a bell-shaped curve. For high bandwidth, the maximum reflectivity is around 67%. Typical values for layer thickness control and lateral uniformity are below 0.2%, and the coating stress shall not be greater than 100 megapascal. The coating shall also work at temperatures up to 200 degrees Celsius. Coatings behave very differently when you move from deep UV to EUV. Let us have a look at the situation in deep UV first. Considering an uncoated lens element, about 92% of the incident DUV light is transmitted, while the remaining 8% are reflected at the front and back surfaces. By means of anti-reflectance coatings on both surfaces, making use of destructive interference, the losses due to reflectance can practically be reduced to zero at the expense of some absorption in these coatings. In total, still the transmission can be increased roughly from 92% to 99%. Let us have a look at EUV. In contrast to this, both transmission and reflectance of an EUV beam incident on an arbitrary uncoated lens element or mirror surface substrate are zero. The EUV radiation is completely absorbed within the first micrometer of the material. Only if the substrate is coated with a multilayer coating consisting of alternating layers having high and low index refraction, a considerable part of the incoming light is reflected, this time by constructive interference. For a wavelength of 13.5 nanometers, multilayers based on molybdenum and silicon have proven to yield the highest peak reflectance. The theoretical maximum for this is 75%, while in practice the reflectance can be higher than 70%. The deep UV transmission is significantly higher compared to the EUV reflectance. Real coatings have lower reflectance and spectral and angular acceptance than the ideal multilayer. The picture on the left shows a TEM cross-section of a MoSi multilayer. The interfaces between the Mo and the Z layers are not ideally sharp, but exhibit a transition zone in which the concentration of the two materials changes gradually. This is partly caused by intermixing due to kinetic energy of the deposited particles hitting the surface during the deposition process, and partly by the chemical forces favoring the formation of molybdenum silicides. Another cause for low reflectance is the crystallinity of molybdenum films, leading to a certain high spatial frequency roughness of the interface, giving rise to large angle scattering. Interdiffusion and roughness effectively reduce the contrast of refractive index, causing a reduction of the peak reflectance and the width of the back peak. One of the means to increase the index contrast at the interfaces between the high and low index material is the introduction of thin barrier layers. Such barrier layers consist of elements with low EUV absorption like boron, carbon, silicon, and compounds of these. The gain of reflectance depends critically on the thickness of the barrier. If no barrier is present, the natural diffusion of molybdenum and silicon leads to a mixture zone with a certain thickness, leading to a certain index contrast loss. In case of a barrier which is thinner than the natural mixture zone, the index contrast is improved. If the barrier layer is made thicker, the index contrast is reduced again and reflectance is lost again. It turns out that there is a narrow regime of barrier layer thicknesses where the contrast is best. Effective barrier layers can enhance the peak reflectance by 1 to 2%. Also, the roughness of the surface on which the multilayer is coated leads to a reduced reflectance. To reduce the surface roughness of the substrate, either the polishing can be improved or the rough substrate can be coated with a smoothing layer. If the energy of the particles on the surface is low, the lateral mobility is also low and the layer tends to roughening. With higher particle energies, the mobility is increased and particles are more likely to travel from a hill down into a valley, thereby creating a smoother surface. I already explained that the surface of a mirror in an EUV lithography tool has to meet demands in all three spatial frequency domains, namely figure, MSFR and HSFR. The EUV coating can change these properties. In the MSFR, the PSD is largely replicated by the coating, while the HSFR is subject to roughening or smoothing depending on the coating process parameters. Long-range figure errors are induced by the coating via the coating stress and the lateral layer thickness gradients. This closes the discussion on the optics production. An EUV system also consists of a lot of mechanical and mechatronical components. So let us have a quick look at one mechatronical aspect of an EUV system. Not only must the surface be produced with a sub-nanometer accuracy, but the mirrors themselves must be positioned with sub-nanometer and sub-nanorad accuracy within the optical column, and that is during operation in the scanner. This performance is achieved because the position of the mirrors is continuously measured, and this information is feedbacked into actuators that hold and move the mirror. Depicted is a test module for EUV mirror positioning. To visualize what the specification of nanorad means, you could use the following analogy. If you would inflate the situation to the distance Earth to Moon, you could control the position of an image on the Moon with less than 20 centimeters accuracy. These were only a few examples demonstrating that it is really leading-edge technology that make these EUV systems possible. That concludes our introductory course into EUV optics. Thank you for watching.